I'd like to introduce Professor Paul Alivisatos. He did his graduate work here in chemistry, and before going on to Bell Lab, where he, from then on, had a very distinguished career as a scientist. He was the previous director of the Molecular Foundry up at LBL, and is currently the director of Material Science Division up at Lawrence Berkeley National Lab. He also is a professor here in chemistry and AS&T. And recently at last May, he won the Telgas Award, a rather famous and large European prize in science. And today he's going to be talking about, let me get this right, nanocrystal molecules.
Okay.
So please give a welcome to Professor Paul Alivisatos. Thank you.
Okay. Thanks so much. It's a pleasure to be here to share some recent experiments with you. I'll show two recent experiments from my group, and I'll try to tie them together into a theme that I hope you will find of interest. So the experiments that I'm going to show relate to what I'm calling nanocrystal molecules. And so let me start that off by explaining the basic idea. What we have are small crystals. Let me see, I'm not sure if I saw a pointer. That's the only detail I didn't check in advance. Do we have a laser pointer? Or if not, I have one, so let me just grab it. Excuse me for a moment while I just do it. So in the work that I'm going to describe, our goal is to take small crystals and bring them into proximity with each other. And we think of these small crystals as being artificial atoms. So each one of these has a certain physical property when it is independent and isolated from other species. And our goal is to make little molecules out of those, molecules being in the sense that the atoms are brought into close proximity with each other with different symmetries and arrangements in space. And then to examine the properties of those groupings. And in the first experiment, I'll show you two versions of that. And in the first ones, the linker molecules will be DNA. Okay? And the reason for choosing the DNA is because once we've attached DNA onto the particle, the code that the DNA sequence designates can be used to create any arbitrary patterning of particles. So it has a programmability to it that allows us to build up a variety of molecules in that way. And so let's think a little bit about this idea. I'll show you two manifestations of nanocrystal molecules. And in the first one, the thing that brings the particles together is DNA, as I just mentioned to you. And in the second one, it will be a type of inorganic crystal, which we make branched. And then that allows us to grow things off the edges that we would like to. Now, the question would be, for these to be called molecules, to my mind at least, I would think of them as then, if I think of this as an atom, then when I bring it together into a molecule, what would be interesting certainly would be if this entity, where four particles are brought together, has completely different properties than just the independent ones of the individual elements. So you'd like a dimer to be distinct from two monomers, and a trimer, yet again, different each time to have a completely different set of properties. Otherwise, it's not as interesting, and we don't need to call them molecules. But fortunately, they do have that property, and the reason is because in this first case that I'll show you, it will be a through-space coupling. The DNA will only create a spatial arrangement, but the particles will couple to each other via the plasmons. And I'll try to explain to you a little bit about plasmons as we go along. But the simple idea is that when light is incident on one of these particles, it produces an oscillation inside of the valence electrons. And a metal particle is just very polarizable. So that kind of sloshing around of the electrons in one particle produces locally a field, which in fact induces polarization in the adjacent particle, which comes back, and so on. So they feed back on each other. When two particles are close to each other, they'll behave very differently with respect to electromagnetic radiation than just one. So first of all, just to show you how the molecules are made, we typically start, in this case, with a gold nanoparticle, and then we add a DNA strand onto it with a thiol on the end. So somehow at the end here we link a DNA strand. And what you can see here is that if we run these through porous medium in an electric field, then the naked particle will run at a certain speed through this agarose gel, but when there's a DNA attached, it will run more slowly. And if there are two DNA strands attached, it will run even more slowly. And you can go in and slice these things out and collect them, and then you can do whatever else it is you want to do with them. Or in more recent versions, you use liquid chromatography, where you get very clean separations of these bands, so that those are then units that you can subsequently build more molecules with. And this gets better when you have two particles. For example, if you run through a gel and you've got a gold particle, then with DNA you add a second one, the mobility in the gel changes a lot more when there are two particles than when there's just one plus DNA. It makes a much bigger difference. So now these become very distinct entities that you can separate quite easily. So these would be, for example, some of the more complicated molecules that we've made. These have a so-called quantum dot. That's a semiconductor particle, which I'm not going to really describe too much in this talk, but we worked on for many years. So it's a small semiconductor particle here. It's slightly elongated, has an aspect ratio of about 2 to 1. And here it's attached, a semiconductor particle, to one gold. Or here you can see a semiconductor particle attached to 2 golds, 3, 4. And so that's why I count these as being nanocrystal molecules. These are quantum dot gold N, where gold varies from 1 up to 4. And so then they become an interesting set of species to investigate. Now, it turns out these are too complicated for their properties for me to describe to you at the moment. And in fact, I'm not even sure I understand them personally. So we're just going to do the dimer first. So let me just show you the properties of two particles when they're irradiated with light. And I'll try to show you how the fact that the particles couple so strongly to each other can be used to make a kind of molecular ruler, which will in turn allow us to study the fluctuations of the DNA. So, to the plasmons. As I mentioned to you a moment ago, when light is incident on one metal particle, it polarizes it a great deal. And it turns out it has a resonance in the visible region of the spectrum if it's gold, or in the blue region if it's a silver particle. And that resonance is quite intense. It's really, if you have a 10 nanometer particle, it's a very, very intense scattering that you can see in a dark field microscope, for example, quite easily. So one particle, if it's independent from any other and far away, has a simple resonance. But if you bring two particles together, it's a lot like coupled springs, and the plasmon resonance will split. You get a red shifted and a blue shifted, or a lower and higher energy mode. The lower energy mode is a longitudinal plasmon, where the direction of the oscillation of the polarization is along the axis between the two particles. And there's also a transverse mode up at higher frequency. And the oscillator strength is renormalized in this pair, as you probably are familiar with other types of oscillators. If you look at the polarizability of a pair of particles, it's a lot larger than the polarizability of two separate particles. So, for example, in the limit where these two are practically touching in a simple model, the polarizability of this pair would be 4 times that of one particle. So when you bring the two particles together, what you expect is to see a split in the spectrum, one carrying a lot more intensity than the other, and that's what's expected in just a very simple model. So here's just an example of doing something like that without DNA now, just putting particles on a substrate. This is a silicon nitride substrate, and particles have been scattered on it randomly. They aggregate. And you can just, in electron microscopy, you can see the particles. Here's 4, here's 1, here's 2, and so on. And then you can go and do dark field microscopy. In dark field microscopy, the light comes from the edges of the microscope objective. So it's got a kind of a ring on the outside that brings the incident light from a very steep angle. And if there's a particle there and it scatters, it sends light right up the microscope objective. So you see scattering, and you can take color pictures of that. So here you can see, for example, each one of these arrangements of gold particles produces a different color and a different intensity. So that's the proof that we have nanocrystal molecules, each of which is distinct from all of the others, and that you could build ultimately a family of probes that you could use. For example, you can send these anywhere you want inside a cell or someplace else and look at them, and you'd see a special color coming from that particular object. So it becomes a very valuable unit for us. Now, there's a lot of work that we've done over many years with my colleague Jan Lippard in physics. So here you can see an example. This is a silver particle, and it's sitting on a substrate. And then a second silver particle is brought in with a DNA strand so that the two will couple with each other, right? So here you go from one particle to two, okay? And you can see that when you go from one to two individual particles, the spectrum shifts. You see these are not, they're not scaled particularly. You can see it's much brighter when there are two there, but it shifts. You can see the higher energy mode that has less oscillator strength. In the case of gold also, you can see the binding and the shift of the spectrum. In the case of gold, the spectra are broader, so you only see the transverse mode as a kind of a little shoulder. Okay? So you can see then that if we use DNA to bring two particles together, we can readily see the action of going from one to two, and it makes a little molecule. And the first thing that you would expect is that this coupling between the particles should depend on the distance. So here you can see the resonant frequency of the plasmon pair as a function of the distance between the particles based on changing the length of the DNA. And what you see is that the spectrum changes roughly over the diameter, when the particles are changing in distance from each other, over roughly their diameter. So if they're 5 diameters apart, the motion of the particle doesn't matter at all. But if they're within 1 diameter and they're moving around, the spectrum will be changing all the time as they flop about. Okay? So it becomes very sensitive in that respect. So here's an experiment where we can use that to study how an enzyme cuts DNA. This is the EcoR5 restriction enzyme. It's a very classic enzyme. If you have a molecular biology textbook, it probably has this picture in it without the gold particles. But it's well known that the enzyme will bind to a specific DNA sequence that you can program into this pair, and it will cut the DNA. That's why it's called a restriction enzyme. It cuts the DNA. And very interestingly for us, that takes you from 2 particles to 1. So we should see it very clearly, the cutting events. But more interestingly, it's been studied for many years, and it's known that the enzyme will first bend the DNA and then cut it. That's known from experiments which you can change the salts that are present, and depending on what salt is present, you can trap the enzyme in the bent state without having it cut, and then see that it's in fact bent. So in our experiments, we're going to try to just watch the cutting event, and it should be very easy to see the cuts, and then we're going to try to see, can we watch the enzyme bend the DNA? Can we see that happen with the plasmon ruler? That'd be a good example of a nanocrystal molecule doing something useful for us. So in this image, what you see is lots of particles. There's some big things which are dust or something. But there you see lots of particles here, like this and this and this, so on. Each one of those is a dimer, 2 particles joined together. One is affixed to the surface. Then there's a DNA, and there's a second particle. The enzyme has been introduced. And when the enzyme cuts, you'll see 1 particle leave. Okay? So here's the movie. You can kind of get a feeling for it. And you see these twinkling events, right? You see them all twinkle a little bit. And each one, and if you have the concentration to do it, like I'll look at that one right there. Oh, when it cuts, if you look very carefully, you might be able to see the first particle is still there, okay, but the second one has left, and you can see there's a color change and the intensity changes. And this is a nice kind of experiment for me. I like it because one of the things that goes on these days is a desire in a lot of molecular phenomena to look at single molecules. But at the same time, you can't learn anything about single molecules unless you look at enough of them. So here we collect every single trajectory, but on lots of them. So we can then go through and try to see, is any given trajectory actually statistically significant? What are the averages? How do these things behave in a systematic way? So if you look at those cutting events, you'd see a plasmon resonance. This is the spectrum plotted in this axis here as a function of the time. That's the cut. Or here's the intensity, and then there's the cut. And you'll notice here that this is kind of dropping in intensity all along here, and that's because poor Sasan and Bjorn, Sasan Shekhol Islami and Bjorn Reinhardt, who were doing this at the early days of doing this, the microscope objective kept kind of, the microscope stage would kind of move out of focus slowly. So that's kind of losing focus. There's the cut and so on. They got much better at that later. I also mentioned on here no blinking or bleaching. These gold particles are really fun because, in fact, they scatter light very intensely, but they're the only single molecule probe I know of that has no blinking and no bleaching. They don't go to some other excited state. They don't turn off. They don't get tired. You can look at them for as long as you have the patience to look. Now, here are some trajectories. This is how the data comes off the scan, and then these are 10-point smooths. There's 6 scans, just 6 trajectories on here for you to see. And what you can see is, for example, here is the before, and there's the after. That's the cut. Here's the before, that's the after, that's the cut, and so on. And if you look, you can pretty consistently see that the cut is a sharp event. And if you look, you can also see that the noise here is generally greater than the amount of noise here. And that's, let's look at it, be careful and try to look at that. This probably comes from the instrument and maybe even the particle bouncing up and down on the substrate a little bit, but mainly from the instrument. But here, there's an additional contribution to the change in intensity, which comes from the fact that the 2 particles are jiggling around. And so as the 2 particles jiggle around, their polarizability is changing. So now we're looking at how this DNA is joining the particles and fluctuating, and we're seeing that. And you'll notice here that typically just before a cut, the intensity is a little bit greater than it is way before the cut. Typically there's just a little plateau, a little elevation of the signal in the time interval just before the cut. And that is the DNA bending by the enzyme. Remember, the DNA is sitting there, the enzyme binds to it, and it bends. And when it bends, the particles get closer together. When it gets closer together, the polarizability increases. When the polarizability increases, the intensity and the scattering goes up. Then there's a cut, and so on. And you can follow and track these events. So that's what we see with this so-called plasmon ruler. You can kind of see the particles bouncing around. It bends, it gets cut, and so on. And it's a kind of a fun game. One of the things that's worrying us, and which maybe you would have noticed when we try to build our nanocrystal molecules, is that they're a little bit on the floppy side. And so sometimes that is causes some disappointment. You know, you'd like to be able to place molecules, atoms inside molecules precisely. Although, in truth, if you look at all possible molecules, there are many in which the atoms are floppy. But you know, it's sometimes when you want to build something, you'd like things to stay put. And so that's a motivation, as I'll show you in a little while later, for building an inorganic scaffolding that's rigid for holding the particles in place. But the fact is that the DNA is flopping around quite a bit. And so we've been doing a study now for a few years with Alex Mastriani on just trying to characterize those distributions of distances by small angle X-ray scattering. So as you probably know, if I have one particle and it scatters X-rays, you'll see a typical scattering pattern which will be related to the size of the particle. But if there are 2 particles, one will scatter X-rays towards the other and then back again, so there's an extra interference that will take place, and that will be characteristic of the spacing between the 2 particles. And the advantage of this technique is that it's not model dependent. I don't have to tell you anything about plasmons and so on. It's just something that happens because there's electron density there. A very simple model can explain it. And so we can use that model and transform the data and look at the distribution of distances between 2 gold particles as a function of the length of the DNA. And it's actually quite interesting. This is the distribution of distances. All these curves correspond to different ACGT content, which changes a little bit the rigidity of the DNA, and also slightly different salt concentrations. But basically, you can change the length of the DNA, and you can see that the two particles get further and further apart. But I'm sure you also notice that as the DNA gets long, you get this enormous long tail of the distribution. So what it says is the DNA is kind of floppy, and the particles, as the DNA gets longer and longer, it bends a lot, and the particles spend a lot of time close to each other, even though if the DNA was maximally stretched, they'd be much further apart. And that's a kind of an interesting thing to study. And so, we can make different models for it. And it turns out that if you look in your molecular biology textbook, they'll describe the double-stranded DNA with what's called a worm-like chain model. They just have little links inside the chain, and they allow it to bend to different angles depending on the chain segments can bend to different angles depending on the stiffness of the polymer. A worm-like chain is a classical statistical mechanical model for a polymer species. And so we can take the persistence length that's published, it's out there, it's in the textbook for DNA, and try to describe with it the distances between our particles. And we're doing this with David Sivak, a student working very closely with my theory colleague, Professor Phil Geisler. And the fact is that it doesn't match our experiments terribly well. And to make a long story short, and not wanting to go into all the details of it, I think what I'm going to do is just show you this movie, because the movie is kind of a good way to see it. This is a model where the DNA is a double strand and a worm-like chain. And it's about the scales of what we used in the small-angle X-ray scattering experiment. And you can see it's kind of flopping around. And this is using the persistence length that you'd find in your textbook. But in fact, when we measure the distribution of distances and we use this model, it doesn't look anything like the distribution we see. The particles are too far apart. So what, in fact, David and Phil believe is going on is that the DNA, as you know, it's double-stranded. And when it's double-stranded, it's more rigid, has a longer persistence length. But the binding between the base pairs in the DNA is kind of weak. So occasionally what will happen is the DNA will just pop open locally. Just for a brief period of time, the base pairs will open up. And at that point, it's actually single-stranded, not double-stranded. And so during that brief period of time, it has a much shorter persistence length, and it bends a lot. And if you include that effect in there, then you can come much closer to describing the full distribution of distances that occur with the two particles. So it's a kind of a fundamental study. Now, you can try very hard to find ways to make the DNA more rigid. Basically, everything that I just showed you is saying DNA flops around a lot. Now, my colleague Ned Seaman at New York University has spent about 30 years now figuring out all kinds of tricks by which you can make DNA strands wrap around each other in very complicated arrangements. And as they get more and more interlocking, there's a hypothesis, at least, that they get to be a great deal more rigid. So we've done some work with him. Here you can see examples where we're depositing particles in arrangements that are on a substrate using these kinds of DNA tiles. And you can see, for example, here big and small particles laid out in a quasi-grid using that more rigid version of DNA. And we would like, of course, to find more versions like that. So, for example, Alex has recently built little pyramids that are putting the gold particles at the vertices of a tetrahedron for particles like that. Here, of course, again, they're just deposited on the substrate. But in principle, this could be a great deal more rigid. And in addition, what we're hoping to do is to put inside the DNA the sequence for cutting by that enzyme again and come in and do the cut. But this time, we won't be measuring just the distance between two particles. We can measure the distance between every group of particles, every pair of particles, so that when the DNA comes and cuts, we'll be able to see not just the distance changing, but if, for example, there's a twist or a reorientation in 3 dimensions, by looking at all the pairwise particle separations, we should be able to see something of that type. I'm going to switch now to another kind of nanocrystal molecule. There's many other examples of these, which I won't go through with you, with DNA and particles, and I think it's kind of an aside, so I don't want to do too much on that. And you excuse me for switching to another kind of molecule, which I hope you'll find entertaining. And these have to do with particles that have branches inside them, and where we can grow gold on the ends of a branched particle. Okay? So first of all, about the branching. This is the packing of atoms in a tetrahedrally bonded semiconductor. Okay? This would be, for example, for cadmium selenide, which is a material that we frequently use because it has a visible band gap and shows beautiful size-dependent spectra. But this would also be for gallium arsenide or indium phosphide, a variety of semiconductors that you might encounter that are tetrahedrally bonded. In other words, one atom is bonded to 4 others. And you can see a certain stacking sequence here. And if we like, we can go from one where there's this kind of ABC stacking of planes, ABC stacking of planes, to one where there's an AB-AB stacking of planes. And what we discovered a few years ago was that this could be used to create branch points because these two stackings, which both have tetrahedral bonding of atoms, share one crystal face in common. So these are examples of these so-called tetrapods that you can see here. These are little crystals with 4 atoms, with 4 arms at the tetrahedral angle. And the 4th arm, let me see where I could show you that. You see the bright spot in the electrons. There's 3 arms there, and then there's a 4th one sticking out of the page. So these are little objects with arms projecting out. And if you ever, probably a lot of you don't ever have to take a chemistry class, or maybe you did take a chemistry class at some point, I don't know. But if you did, you had to have a molecular model set, and you could build your models. And one of the more prized pieces, which you didn't get as many of in your model set typically, would be the tetrahedral carbon that you could build things out of, right? And so for us, when we saw by accident first that we could make some of these particles at very low yield, we thought, okay, this is going to be great for building nanocrystal molecules because it's an object which spontaneously creates the symmetry that a carbon atom would create, and we can use it to subsequently, by scaffolding, build other pieces on top of, and in this way make other kinds of molecules. So we spent a great deal of time learning how to make these in high yield and to control the lengths and the widths and so on, and to make them, kind of viable. I won't go into that. Here's some examples of recent ones where we got even better at it. This is an example of a little zinc blende seed. So this has the ABC stacking of atoms, and this is a wurtzite seed. It has the AB-AB stacking of atoms. And we can isolate those and then grow the arms on top of them. So here you can see that if I start with the little zinc blende piece, then I grow my tetrahedral arms. If I start with the wurtzite piece, then I grow rods, which have pieces coming out the front and the back. So there's the little seed piece and the 2 pieces that come out the sides, whereas here it branches in this way. The little seed here is the semiconductor cadmium selenide with this band gap, and the branches or the longer arms are made out of cadmium sulfide, different materials. So you start with a seed and then you grow these arms on it. And what's interesting about it is these have different band gaps. So when light is incident on these things, you make electron hole pairs, but the holes will, for example, stay in the little cad selenide piece in the center, whereas the electrons will run around the whole thing because the potentials are just made in that way. And you can see that if you do elemental analysis and so on, they really do have the selenium piece in the center and the sulfides on the arms. And so, for example, you can look at the fluorescence lifetime of these things, and what you see is that the fluorescence decay depends on the length of the arms. And you could understand that from the fact that in this material, when it emits light, you make an electron in a hole, when it emits light, they recombine, but the rate at which they'll recombine depends on how well they overlap. So if, for example, you grow that arm longer and longer, quantum mechanically, the electron is delocalizing over that whole arm, whereas the hole is sitting in the center. So as you make the arms longer and longer, you can see the radiative rate becoming slower as the system has this separation of electrons and holes. So, these things show lots of interesting, I would call these nanocrystal molecule-like behaviors. And here you can see another example of the kinds of things which motivate us in terms of the chemistry that we're interested in. We can make, for example, second branches. There's one branch in the center, but then we can come in later and make a second branch. And so if you're familiar, for example, in the area of polymers, for many years people just studied linear polymers. And then maybe 15 years ago or so, Professor Frichet here in chemistry was one of the world's leaders in thinking about polymers which would branch and make so-called dendrimers. Well, these are inorganic branched structures. So we again think of them as kind of a nanocrystal molecule with this branchy structure that's three-dimensional and where we can control the generations of the branching. We can study these electrically. Here you can see examples where we take a rod and we put electrodes on it, or we can take a branch one where some of the branches broke, or we can have a whole tetrapod, and we can take a tetrapod on a surface and we can evaporate electrodes on it. So if we want to study these as nanocrystal molecules, we also can study them electrically, not just optically. I showed you in the plasmons optical studies of nanocrystal molecules, but in these nanocrystal molecules, electrical studies are especially interesting to us. So I'll just tell you very briefly a couple of words about the electrical things that happen. You may or may not know that there are many scaling laws for small objects, and the most famous scaling law for a small object is probably the reduction of the melting temperature, but maybe the second most famous one concerns charging energy. Let's say you've got a little object and you stick one charge on it. Okay? It turns out you've increased the charge density by one charge over the volume of that object. Okay? Now, that makes the average Coulomb repulsion inside there a little bit greater because there's one extra charge. So if you make the object smaller and smaller and smaller, the charge density is increasing. It's only one charge added, but because it's divided over the volume and the crystal's getting smaller, actually the Coulomb repulsion becomes greater and greater as the object gets smaller. So it's a very famous law that if you try to add a charge to a small object, you've got to pay the charging energy. And so what you see typically, if you look at a source drain versus gate voltage kind of curve of conductance in a small object, is you see that there are regions where no current will flow because you haven't overcome yet the charging energy. And that makes these so-called Coulomb diamonds. So you can see these here. And this is the charging of a single nanorod. If you just look at the nanorod, all you see are these beautiful Coulomb diamonds corresponding to the size of the object that's being charged. If, on the other hand, you look at one of these branchy guys, you see diamonds here which have large and small sizes. You see big diamonds and then little diamonds in an intricate pattern. It doesn't look like one charging energy now. It looks like a series of different charging energies of different sizes. And the way that comes about is big diamonds in these things come from charging the center object, and little diamonds come from charging the arms. And if you look at the quantum levels of this tetrapod, you can see some electronic energy levels localize states in the interior, whereas other higher energy states will localize charges into the arms, which are much bigger. And that's why when you have the branchy structure, you'll see this pattern consisting of small and large diamonds, whereas in the simple rod, you'll only see one pattern. And if you look at these images, those are nanocrystal molecules also. If you've ever remember from a chemistry class, you would have learned to look at your molecular orbitals. These look just like the molecular orbitals of a molecule, except they're in objects that are, say, 1,000 times larger or something like that. And that's why we think of them again as nanocrystal molecules. I think I'll conclude there, just having shown you these two examples. We've also grown gold on the ends of these things, but I won't go there for now. I think you just get a feeling here of two examples of kind of nanocrystal molecules, one where we use DNA and another one where we use an inorganic scaffolding in order to create the spatial arrangements. And there's a series of others. Once you've seen these two, you can create other lists of them. You could have used proteins. Here they don't have to be branches. There's lots of things of that you can do. But it gives you a feeling, at least, for kind of our thinking about how we go about making these kinds of species that consist of small numbers of coupled nanoscale objects. And I think I listed a lot of colleagues on there in my acknowledgments. Maybe I'll put up some of the names here as well. In the plasma and ruler stuff, many, many people have participated over quite a long time. Karsten Sönishin, Björn Reinhardt, Sasan Sheikh-ul-Islami, Alex Mastriani I mentioned, and many, many colleagues that I collaborate with. I didn't show this work. It's a different version of nanocrystal molecule that I didn't get a chance to show. I showed the branches instead. And yeah, open it up for some questions. Thank you for your attention.
Is there any questions?
When you showed those long DNA molecules and how they seemed to bend more than the models had predicted, you said this had to do with breaking of one of the strands. I was wondering whether that is something that you think happens naturally, or whether it happens only when you put these big things on the ends that might...
No. Yeah, I don't think it has anything to do with the particles being there. It's something that is just a characteristic of the binding energy of the DNA. And there are many lines of evidence for that I didn't show here. But one thing I can say is that if you looked at those ones where we cut the DNA with the enzyme, we could measure the rate at which the enzyme cuts the DNA. And it's exactly, it's within a few percent of the rate that's been measured in bulk solution by other techniques. So the gold particles are really not perturbing too much the dynamical motions of the DNA. And part of that is because the particles have a negative charge, so they kind of repel the DNA, essentially. So DNAs and the ionic strengths are not too far from what would be there under normal, they really are the ones that the DNA normally likes to function at. So I really think we're not perturbing the DNA too much, and we're looking for good, as many examples as we can where we can test that and just make sure that it's true. But so far, that's what's held up to be the case.
On the same subject, when those DNA buckle, do you ever try corresponding that the buckling angle to a well-known angle in mechanical engineering of just a cantilever or a rod buckling, and it'll give you a set angle?
Well, these are spontaneous thermal motions, and essentially what I guess, let me try to say it a slightly different way. If I have a polymer strand in statistical mechanics, it's going to have its motions. If it's got a certain persistence length, it'll have spontaneously its regular motions. And the way DNA is ordinarily described is that once it's a double-stranded DNA, it has a characteristic persistence length. And I think what we're trying to say here is it doesn't really have it's a more complicated molecule because, of course, the two strands can come together, and one strand has a very different persistence length than two, and when it pops open locally, it really behaves as though it has two distinct persistence lengths at the same time. I don't know whether it buckles in the way that mechanically we would think of if we take a rod and just press on it and eventually it will bend. Yeah, I think these are thermal motions which are occurring because the DNA is kind of soft. I will say that if you take, for example, not shown here, but we can take those, the inorganic one, okay, that has the arms, and come in with a force microscope and just push on it. And then you can measure what force does it take before it does exactly what you're saying and break. And in fact, even there are versions where those things can be imaged and so on. And it's very interesting. So the inorganic ones, I think, are a much more rigid object where the kind of experiment you're describing pertains. But the DNA, I believe, is just intrinsically floppy, and you're just seeing it thermally fluctuate.
So any more questions?
So have you seen branching that's more than tetrapod-like? Like they have more branches than 4?
Yeah. Sure. So that tetrapod we think of as having a branch point that makes this little tetrahedron. Mm-hmm. But it's possible, for example, for that little interior piece to be twinned, in which case you can get more arms coming out. And there are examples where you can see that. We also can make them branch randomly, not shown here, but we can tweak the reaction conditions such that as the crystal's growing, every so often it just branches. And that looks like a, what do you call those things, a sea urchin. If you look at them, they look a lot like that. It's kind of branches all over the place. And you can that's a statistical branching process instead of a deterministic one. And if you like, in those, you can tweak the branchiness such that the patterns that emerge will look like different trees. Okay, they'll have open or closed things and so on. So you can create a wide pattern of branchinesses if you so desire. And it's not just this material. I mean, we've worked out branchiness here. But subsequent to that, we've seen branching, for example, in our group in titanium dioxide and other materials like that. Many groups have seen some branching in metals like palladium and stuff like that. So, you know, there are fundamental mechanisms by which crystals can make branchy structures. And I think it's now that people start to see that as being something where you could control it systematically such that you might get generations and, you know, and make your own selected pattern of branchiness. Yeah.
I'd be interested to hear some of your ideas as far as applications, especially for this inorganic kind of stuff, your molecules.
Yeah. Well, I purposely didn't go to applications today, mainly because I feel like the field that I inhabit is has a lot of applications, and often people shy away from discussing why they are interested individually in kind of the fundamentals. So I tried to show you kind of from a chemist's perspective why I find this space to be one I like to play around in on a more fundamental level. But these materials have, I mean, first of all, the ordinary semiconductor particles that emit light really have enormous application in biomedical imaging, and it's a commercial product that actually, you know, came in many ways out of our research group, and people use them widely. So there's an application there. But we've been working for a long time for these in photovoltaics. And I believe the inorganic materials I described to you, that's where their home is going to be ultimately, because the ways by which we make these particles are rather low cost, and they can be scaled in much. The way you make one of these particles does not look that different than the way you would make plastic. And so they can be, even though they're inorganic, they can be made in large scale. And we've done a lot of work in the group over the years making solar cells with these kinds of particles. And I think that's probably their most direct home, because that's an application where you, I think the niche that these materials fill, I mean, there's the one hand in biology where inorganic materials are going inside cells, so that's something you can't do with conventional materials that easily, and where the inorganics have advantage. But if you want to find a kind of an electronics type of application, it has to be in something where you need huge volumes but low cost, because that's really what these things naturally lend themselves to. And that's in the energy arena. There's a whole bunch of those, and especially photovoltaics, I think, are the one that are the most serious one.
Is there any more questions? A couple in the back.
I have two questions. For your inorganic molecular structure, what's the smallest feature size we can make? What's the smallest molecular size? And do you have any other idea to make different kind of molecular, something like some chiral molecule?
The smallest ones we make, so the building blocks being the nanocrystals, so we think of those individual crystals as being the atoms. Typically, we don't go much below 2 nanometers in size for those, mainly because our best analytical tool is electron microscopy, and it just gets really hard to see things below there. So although we can make things smaller than that, we typically stick with 2 nanometers and above. It's by habit. It's not an absolute requirement, but that's really where we tend to do the work. The other question was, do we want to make bigger objects? Yeah, look, I mean, there's a whole field where colleagues around the world have taken an individual type of nanoparticle, made it very narrow in size distribution, and if you remove the solvent, it will make a supercrystal of particles. And if you take two kinds of particle, it'll make a supercrystal of 2 or 3, and you can make artificial solids where the atoms that build up the solid are nanocrystals. And that's a whole area of research. There are many research groups working in it, and it's a very interesting field. Those kinds of artificial solids have their own sets of properties. So I view us as kind of making the molecular version that are the cousins of those artificial solids. And it's a whole field. There's a lot of people working in it. I can try to point you in that direction if you're interested.
Are the legs of the inorganic dendrimers necessarily the same length? And if not, is that something that you can control, for example, to make one arm longer than the other?
Uh-huh. Yeah. Okay. First of all, the way we were growing them there, they tend to grow at about the same rate. Now, if you leave them for a long time, warm, and without a lot of atoms for them to grow, what will happen is one arm will grow at the expense of the others, and it will chew them up, and you'll end up with an anisotropic structure in that way. But of course, it would be better if you could instead really control it such that you could choose which arm was longer and which one was not. And that's the kind of thing that I find entertaining. So, for example, we have a scheme in our minds that we've imagined over quite a while where we might be able to put something on the surface end of some of the faces such that they would be blocked, and then grow one, and then remove that and do something else. And if I used a chemistry language, I would think of that as, quote, protection and deprotection, which is something that they do all the time in a chemical synthesis. And we've made versions of that on the blackboard, and I think it's possible to do, but I don't think there's not a whole lot of it. But essentially, another way of thinking of that would be the carbon atom has all 4 arms the same, and in synthetic chemistry, one of the most interesting things is to make chiral ones where each arm is distinct. I think we can make those also. I'd say it's possible to do those things. Not a whole lot of it has been done. Yeah.
Are there any more questions? Then let's thank Professor Alivisatos again. Thank you.